Hello everyone. Yeah, so I'm back with another stream, and yeah, guys, whoever is watching for the first time, let me just give you a bit of a context. So yeah, my name is Satyam, and basically I am interested in all things zero knowledge, and my goal with these sort of streams, long streams, is try to make sense of this overall ecosystem. And as I am, I am working remotely, and I don't have access to, real teams, real people, in person. So I thought the best way to learn about these technologies is doing, building in public. So that's the whole goal of doing these streams, to basically talking out loud of my thoughts, my inner process, and basically try to make a mental model of all these technologies, all these ZK projects and the underlying tech, and yeah, write a program about it. So that's just me. I don't I'm not really sure if anybody would be watching these streams, but yeah, I mean, if you are interested in ZK and want to build together, just yeah, reach out to me, and we can learn together. Okay, so that's pretty much all of my rambling. Now we are going to explore this project RISC Zero. To be honest, RISC Zero is on my radar for quite some time. So I know that they are one of the best teams in the ZK ecosystem. And yeah, I've been keep hearing about these guys, and there are a couple of good projects, that people are building with RISC Zero. So I just thought, I'll start with it. Okay, so we are on the RISC Zero landing page. Okay, so let's click on start building. Okay, introduction. Welcome to the RISC Zero documentation. RISC Zero is creating the infrastructure and tooling necessary for developers around the globe to build software that leverages GK technology. Nice. ZK technology is staged to reshape the way we interact digitally. Historically, the only method for confirming the correct execution of a software application was through redundant computation. Yeah, I've been keep hearing this analogy again and again, and especially in the blockchain world, when we read the importance of ZK in scaling the blockchain, right? So basically, in the blockchain, all the other nodes verifies if this transaction is correct is by doing this re-execution. Like, somebody is doing a transaction that says that factorial of 5 is 120, and all the other nodes on the blockchain, they will have to again compute the factorial 5 120 in order to be come to a consensus that okay, the factorial of 5 is 120. And this is like a lot of waste of computation, and ZK is essentially solving that. It's basically somehow proves to you that okay, factorial 5 is 120, and without you having to re-execute it, right? So that's essentially saving a lot of re-execution. So yeah, that's one of the use cases of ZK. So I'm already familiar with it. Just made sense to revise it again. Okay, it's now possible to pair a program's output with a self-certifying receipt, mhm, allowing a skeptical third party to verify correct execution, and the verifier doesn't need to repeat the original computation or even see the inputs to the program. Okay, what does RISC Zero enables? Verifiable computation is a game changer for the resilience and economics of operating the computing infrastructure we all rely on. It creates a number of emergent use cases which we are excited to enable. Key among these are ZK coprocessors, which enable blockchain applications to reduce gas costs by moving the expensive part of their application logic off chain. Okay. And optimistic rollups with ZK fraud proofs, including our work with optimism. That looks very promising. The RISC Zero ZK VM can prove the correct execution of arbitrary code, allowing developers to build ZK applications in mature languages like Rust and C++. The release of the RISC Zero ZK VM marked a major breakthrough in enabling ZK software development. The ZK VM made it possible to build a ZK application without having to build a circuit and without writing it in a custom language. Okay. Just to clarify, these custom languages are like these ZK DSLs, domain specific languages like Sarcom and Noir. So if you are building a circuit with these languages, you are much closer to the real circuits. So there is a less abstraction and I believe improved performance as well. But yeah, everything just like there's everything have a trade-off in software development, right? So you have to learn a new language from the scratch, and the library and tooling ecosystem, it's not there yet. Like compared to the Rust, like it's definitely getting better every day, but it's not there yet. Okay. So by allowing developers to build in Rust and leverage the maturity of the Rust ecosystem, the ZK VM has made it possible for developers to quickly build meaningful ZK applications with no background in advanced mathematics or cryptography. We have built a number of applications and primitives showcasing these capabilities, including Zath, prove the correct construction of an entire Ethereum block or an entire optimism block. Nice. Bonsai Pay, send Ethereum to someone's Gmail address. JSON, prove the contents to some entry in a JSON file while keeping the rest of the data private. Where's Waldo, ZK checkmate, ZK proof of exploit, ECDSA signature verification. These examples are all made possible by leveraging a mature ecosystem. Over 70% of the top 1000 Rust crates work out of the box in the ZK VM. Being able to improve Rust crates is a game changer for the ZK software world. Projects that would take months or years to build or other platforms can be solved trivially on our platform. So they are basically essentially reusing the entire Rust ecosystem. In addition to being far easier to build on, we are also delivering on performance. The ZK VM has GPU acceleration for CUDA and Metal, and with continuations, we have enabled parallel proving of large programs. Okay, getting started. So let's start with the getting started guide. What is this? Get started. To use the ZK VM or Bonsai for blockchain, your user will need to build a ZK VM app, generate proofs for the ZK VM app, integrate proofs into generate proofs for ZK VM application, local proving, dev mode, remote proving, post proofs on chain. Okay, ZK VM quick start. Okay, so we need to now start doing something. Okay, so let's do one thing. Let me open a VS Code. CD Web3 RISC Zero. Okay. So I will take this VS Code here and I'll do one thing. So I'll put it here. Okay, so now we have access to both the things. Okay. So hopefully this would be much better. So we can see, okay, so what do we need to install? These instructions guide you through installing or updating RISC Zero tools to build your own RISC Zero ZK VM projects. You will install the Cargo RISC Zero tool Cargo risk zero. Okay, so there is they have their own package manager for creating and building risk zero ZKVM projects, as well as the RISC Zero toolchain used to build ZKVM guest programs in Rust. Okay, I'm going to write a few questions as well, open questions. So this is just me, like, I was trying to basically make sense of it previously, so just wrote few things that we have already gone through. Okay, open questions. Open questions, and what we are going to do is to this checkbox sort of thing. So as we answer these questions, we'll mark them off. What is guest program? Guest program, because I'm not sure what is guest program. Okay, these instructions give you guide you through installing or updating. Okay, the RISC Zero VM requires Rust. If you don't already have Rust and Rust up installed, start by installing Rust and Desktop. Please follow the recommended Rust installation instruction. Okay, but we already have Rust up, so I don't think we need to go through that. We also, I think, Rust compiler version also is pretty good. It's just 2 month old, 0331. I think we are fine with this. Okay, so now I'm going to install the RZ up. So I'll just type it curl -l https risc0.com. I like typing things. So okay, so this will install. This will just download the binary. Okay, restart yourself or run. So I'll just run this. That's it. Command not found. Okay, so I'll just open a new terminal. We can open new terminal and we can control W. I can just kill this terminal. Kill terminal. Okay. And we do RZ up install. Okay. RZ running RZ up will install the latest released version of RISC Zero toolchain. For a specific version, you can use RZ up install cargo ISO that. Okay. And now we can do RZ up -l for more options. Manual installations and installations for other systems. I don't think. Okay, I think we can just use this as well, because my system is ARM system. So yeah, update when using RZ up in CI environments. So we are not using CI environment. So I think we are good to go. Okay, ZKVM quick start. Welcome to the ZKVM quick start page. Here are the steps to create your first group. Okay, install the RISC Zero toolchain that we have already created a new project with. Uh, we can create a new project with cargo RISC Zero new. Okay, I wanted to do it in here, but that's fine. We can do cargo RISC Zero new and hello RISC. Okay, what it is taking, the cargo RISC Zero tool, the guest name parameter, the guest program that the ZKVM runs to generate a proof of its execution. I'm not sure what this guest name parameter is, so I'll just write down another question. You know, what is this? What is hyphen hyphen guest name parameter? So I believe we need to learn more about this guest program, but for now, I just want to run something. I see something that works. That's my, that's always my immediate goal when starting a new project. So I'll just do the same thing. Hyphen hyphen guest name, guest code for ZK proof. Okay. So we must have something now. We have this. So we have this hello risk now. Okay. Uh, we also have this readme, but that's fine. Uh, we can use this only. So okay. Now what we can do? So we have a new project, and the Hello World tutorial contains step-by instructions on how to share private data between the host and guest, share the guest results with the host publicly, generate a receipt, and read its journal contents. Quick development leveraging dev mode. Okay. During the development of your project, running your take code can take a long time due to the proof generation process. To address the issue and allow for faster iterations of your code, we suggest utilizing demo. This mode bypasses the time-consuming proof generation process. To activate demo, set the environment variable. Uh, okay. Once you have reached a point where you can do so by setting RISC demo mode equals to 0. Okay. Note that proof since okay, so what we are going to do is we are initially going to run things without proof generation. Okay, and this will help, like, this will help things a bit. So because I want to keep the example as simple as possible initially when I'm just playing with it. So I'll just do this 0 dev mode equals to 1. Okay, we get this. Okay, now what it is saying, once you have reached a point when you are ready, so okay, we can enable the proof generation later. Note that since proofs are now being generated, the execution time will be significantly longer than when running in demo. To create a proof with the ZK VM on your own machine, we recommend at least 16 GB of RAM. To avoid these hardware requirements, consider using Bonsai to generate proofs remotely. As it will significantly faster than, you can request access to Bonsai to set additional flags. Okay, to gain insight into your application's performance, you can obtain executor statistics by setting the rest log environment variable to info. Setting this filter will print statistics about the execution before proof generation. So you can understand how computationally expensive your application is. Okay, it's just like, seeing the circuits information. That's what I believe. Yeah. Since the statistics concern only the executor phase, it is recommended to run your application in dev mode to avoid the overhead. The statistics include total cycles, session cycles, segment count. Yeah, I mean in Noir this was gate counts and things like that, but here it's different. Total cycles, session cycles, segments count, execution time. Knowing these statistics is useful for estimating the cost of your application before submitting real workloads to Bonsai, as the cost of proof generation is proportional to the number of cycles and segments used. Okay, so we can now move on to the hello. Okay, building ZK building ZK VM Hello World. This tutorial will walk you through building your first ZK VM application. By following the steps in this guide, you will learn how to use the Cargo Risk Zero tool to create a new project, to send private data to the guest program. The ZKVM executes and generates a proof of a guest program. The guest writes public output. Firstly, visit the installation page. We have already done the installation. Okay, I believe we don't need to do this hello world thing. Okay, so I'm just looking at okay, bonsai, cargo risk zero. I'm just looking at all the things that are there in this particular README file that we generated. Okay, so what we can see here is cargo terminal. Cargo terminal is there. Target is there. Host is there. And yeah, host cargo is there. Okay, what do we need to do? Firstly, visit. Now check the cargo risk zero version. Okay, let's see the cargo risk zero version. Cargo. Okay, I think I need to move my. Okay, so let me just clear this. Okay, cargo. Where I'm typing. It's slow. What? I'm just imagining what will happen when I generate the proof locally. Cargo risk zero hyphen hyphen version. I guess we should be fine with it because we have just installed this. So 2.1.0. Okay. Uh, okay. Second step. Wait. So this is just cargo risk zero. Okay. Git checkout. This is just to see. Okay. What is the version? And can we do cargo run hyphen hyphen release here? Or do I need to clone this again? I believe so. The ZKPM or approver runs on the host. The host code is located on src main.rs. Wait. I guess this is the different code. Okay, let's see just this example and the template that we have got. I think this is different. Examples. So we have this examples and hello world. Yeah, hello world. And cargo run hyphen hyphen release. This is a bit different from the template that we have downloaded actually. Yeah. Yeah, the documentation, first of all, is not uh, sort of in a very, smooth flow. This is like, my first impression of this documentation is because, you know, like as soon as you go through this quick start, you will create a new project, and then they just want you to ditch this entire new project, right? This is not good. This is definitely not good. But anyway, we can do this, rm-rf, because what is the issue is, I want to follow this to the point. That's the problem, right? So okay, so let's just keep this here, okay, and git clone, and we'll need to again open this thing. Open folder. This is definitely not good, but yeah, we don't have a choice, I guess. Okay, so the ZKVM prover or approver runs on the host. The host code is located in, okay, the host code is located in src main hello world src. I'm still believing this is the host code, okay? Main.rs, and the question is, where is this lib.rs? I don't see this lib.rs. Anyway, we are here, so we can just see if we can, open this folder, RISC Zero. Yeah, I mean, we are able to open it. Oh, that is fine. And let's go to the terminal, and let's go to examples and hello world, okay? And we can do cargo RISC zero hyphen version, git checkout release hyphen 2.1, okay? Okay, so we are on the release 2.1, and we then do cargo run hyphen release. Okay, so let's see. This is what it is saying is the host code. The ZKVM or approver runs on the host. The host code is located in src main.rs and src lib.rs. So these two files are the host code. I have no idea what this host code is, okay? But I guess the host creates an executor environment before constructing a prover. The host creates an executor env before constructing a prover. This executor environment is responsible for managing guest readable memory. The host makes the value input available to the guest program before execution by adding input to the like, none of this makes sense to me. Okay, so I guess do we need to go through the overview? Okay, so let's go through the overview. Let's take a step back and go through the overview, because right now none of this thing is making sense. Okay. So I guess part of the problem was we directly jumped to the build section rather than going through the overview of ZKVM. Okay, so let's go to the ZKVM overview. The risk zero knowledge virtual machine lets you prove correct execution of arbitrary Rust code by allowing users to build zero knowledge applications that leverage existing Rust packages. Mhm. Okay, so the RISC zero knowledge virtual machine ZKVM lets you prove correct execution of arbitrary Rust code by allowing users to build zero knowledge applications that leverage existing Rust packages. The RISC Zero ZKVM makes it quick and easy to build powerful, verifiable software applications. To learn more about what this enables, check out our use cases page. If you are ready to start building, check out our ZKVM Quick Start that we already did and that Oracle experience. The ZKVM example applications. Okay, what are the components of a ZKVM application? Okay, the core of a ZKVM application is the guest program. Okay, so the core of a ZKVM application is something called a guest program. Okay, the guest program is part of the application. So the program itself gets proven. To prove correct execution of the guest program, the guest program is compiled to an ELF binary. What is ELF binary? ELF binary, the executable format for RISC-V instruction set. Okay, the executable format of each method in a guest program is written in Rust and compiled into an ELF binary before execution begins. Then the ELF binary is executed and proven. Okay, so the ELF binary is a executable format of RISC-V instruction set. Each method in a guest program is written, and I believe instruction sets are sort of opcodes if I am not incorrect. Okay. RISC-V, the fifth edition of UC Berkeley's reduced instruction set computer architecture. RISC Zero uses RISC-V, specifically the RV32IM instruction set, as the basis for RISC Zero VM. Okay, let's go down this rabbit hole a little bit. Okay. Okay, RISC-V ratified specifications. The RISC-V open standard instruction set architecture defines the fundamental guidelines for designing and implementing RISC-V processors. Assume everything is subject to change. This is like RISC-V instruction set. Okay. I believe we can just assume this is an instruction set, like opcodes for addition and multiplications and things like that. Okay, so we have a ELF binary, which is an executable format for the RISC-V instruction set. Each method in a guest program is written in Rust and compiled into an ELF binary before the execution begins. Okay, that's fine. And now what else? What are the components of ZKVM application? Okay, the executor runs the ELF binary and records the session. So there is something called executor which runs the ELF binary. Okay, the guest program that gets compiled into the ELF binary executable format for the RISC-V instruction set. Executor programs runs the ELF binary, records the session. The prover checks and proves the validity of the session, outputting a receipt. Okay. So the core of a ZKVM application is the guest program. The guest program is the part of the application that gets proven. Okay. You only need to worry about the details of step 2 and step 3 if you are running the ZKVM on your own hardware. If you are using Bonsai for remote proving, then you don't need to write the host code. Okay. Anyone with a copy of the receipt can verify the guest program's execution and read its public shared outputs. That is nice. The verification algorithm receives an image ID as a parameter. The image ID serves as a cryptographic identifier for the expected ELF binary. Okay, deploying a ZKVM application. Once you have built a DKVM application, you can generate proofs on your own machine, or you can make requests to Bonsai to generate proofs as needed. For local proof generation, we recommend a machine with at least 16 GB of RAM. Options for generating proofs using GPU acceleration and skipping proof generations are documented in the feature flags. Okay, check out ZKVM quick start and guest code. Okay, so what is receipt? A brief introduction to ZK RISC Zero receipt. The receipt gives the results of your program, okay, along with proof that they were produced honestly. So when you execute your ZKVM application, the output of your application is included in your receipt. The receipt serves as a succinct validity proof for the execution of your application. A receipt can be passed to third parties and verified in order to cryptographically attest to the validity of your application's output. Okay, so this is just a receipt saying, like, this program was executed correctly. Third party can basically verify. The receipt consists of a journal and a seal. These are two new terms, journal and a seal. The journal attests to the public output of the program, and the seal is the opaque blob that cryptographically attests to the validity of the receipt. It's like a seal, government seal, you know. Seal is the opaque blob that cryptographically attached to the validity of the receipts. How are receipts used? Suppose Alice and Bob have agreed on some computation that needs to get done. In particular, they agreed on some ZKVM guest program, and they each have access to the source code and image ID of the guest program. So the guest program cannot change, right? Like in practice, Bob may retrieve the image ID either by constructing it itself or retrieving it from a trusted channel. Alice runs the ZKVM to generate a receipt, and then Alice sends the receipts to Bob. After receiving the receipt, Bob can inspect the receipt to extract the journal, verify the receipt to ensure that the execution was valid. The guest program that executed was the consistent with the expected image ID. This is all fair. Okay, the journal contains the public outputs of the computation. Users can extract the journal from a receipt using receipt.journal. Verifying the receipt provides cryptographic assurance that the journal was created honestly using the guest program with the expected image ID. Users can verify the receipt using receipt can verify. Serializing and deserializing receipts. For serializing and deserializing, you can use SERDI, which supports many encoding formats. There isn't a one size fits all solution here, but one option is let bytes pin code serialize receipt. Okay, now I think things are making a bit more sense. So just to recap, you have a guest program that gets compiled to the ELF binary. The executor runs the ELF binary and records the session. The prover checks the and proves the validity of the session, outputting a receipt. Receipt have two things, journal and seal. Journal contains the public output, and seal basically cryptographically attached the validity of the receipt. Each guest program have the image ID, and verifier can take the image receipt and check the receipt is for the correct image ID and execution was valid. Okay, guest code 101. In a ZKVM application, the guest code is the code that will be executed and proven by the ZKVM. This page serves as an introduction to writing RISC Zero guest code to help you get started building applications for Bonsai and the ZKVM. For a guide to writing and running a first guest code, check out our ZKVM quick start. For a simple example, check out the Hello World tutorial where the guest receives an input from the host and commits a value to the journal. The full functionality of the guest is documented in the guest module of the RISC Zero ZK VM Crust Crate. Basic basic guest functionality: reading, writing, and committing. Reading, writing, and committing. Okay. To build a ZKVM application, we need our guest program to be able to read inputs, write public outputs to the host, and commit public outputs to the journal. So basic guest functionality: reading, writing, and committing. To build a ZKVM application, we need our guest program to be able to read inputs, write private outputs to the host, private outputs, and commit public outputs to the journal. To support various use cases, there are a number of functions that can be called from the guest for reading, writing, or committing. For a complete list, see the ZK guest module documentation. We include a brief list which should be sufficient for building your first reading inputs: environment read slice, environment stdi. Writing private output: environments write slice, environment std out, environment std error. Committing public outputs to journal: commit slice. Okay, that's like simple enough. Tools for debugging, optimization. There are also a number of functions available to support with debugging and performance analysis. As above, we refer to the guest module for a full list, but include some highlights here: environment, cycle count, and log. Boilerplate before main. In our template and examples, there is a bit of boilerplate code before main. In this section, we explain the each of those lines is and doing. Okay, I think it's the good time to open this. So we are going to again. Okay. So what code they are referring to? Actually, just opening this would be sufficient. Okay, so we can just close this and that's fine because much less heading. So we have in our template and examples, there is a bit of boilerplate code before main. What is this boilerplate code? I don't see any boilerplate code. Maybe in methods, guest, src, main dot. Okay. No std. No std. The guest code should be as lightweight as possible for performance reasons. So since we aren't using std, we exclude it. Okay. No main. The guest code is never launched as a standalone Rust executable, so we specify no main. Okay, makes sense. Okay, I'm going to remove this actually. I mean, in production code, I would definitely keep it, but just for the sake of making this code a little less scary, no main is fine. RISC Zero ZKVM guest entry main. We must make the guest code available for the host to launch. And to do that, we must specify which function to call when the host starts executing this guest code. Okay, we use this Zero ZKVM guest entry macro to indicate the initial environment, which in this case is main. Okay, so at a later stage, we'll try to rename this as well. Okay, so what this is doing, so no main, because Guest code is never launched as a standalone Rust executable, no standard output. Okay, just to make the code for more lightweight for performance reasons. And RISC Zero ZK VM guest entries because host code will launch with this method. Okay, so we are reading the first number from the host. We are reading the second number from the host. We verify that they are not, neither of them are one. Compute the product while being careful. Okay, a dot check mult. Okay, environment dot commit. Okay, so this is the code. This is the guest code. This is very small guest code. That's nice. I like this. Okay, now what do we do? Host code 101. So this is guest code. In ZK, in ZKVM application, the host is a machine that is running the ZKVM. The host is an untrusted agent that sets up ZKVM environment and handles input outputs during execution. Okay, so if you are building for Bonsai, you don't need to write host code. This page serves as an introduction to writing RISC Zero host code to help you get started building applications for ZKVM. For a step-by-step tutorial for writing our own host code, hello world tutorial, all the host functionality is described in the RISC Zero VM ZKVM lesson. Okay, in the ZKVM, a host is responsible for constructing and running the executor and prover. So this is a host. In more detail, the host will construct an execution environment where it will run the executor for a guest program. This environment is where the host will provide settings and communicate with the guest. Run the prover to execute and prove the guest program and generates a receipt. The receipt can now be passed to third party for verification. So in all probabilities, we will not write this host code. I mean, except for learning reasons, but we'll do this for delegated proving, right? So we'll not definitely need to do this. Okay, in a ZKVM application, the host is responsible for constructing and running the executor and the prover. Construct an execution environment where it will be run the executor. Okay, simple host. The code shown below is the main for a simple host program. Aside from the absence of any IO during execution, the host performs exactly the actions described above. This default prover builder build default prover. Okay, where I can find these methods. Definitely not here. I don't know where this host code is here, but that is fine. Now let's see example applications. Okay, we are now on the getting started site. So we will try to make sense of it. So we are on the, okay, the ZKVM, the ZKVM share private data is input with the guest runs on the host. The host code is located in hello world src main dot. Okay, so this is the host code. Tracing subscriber is I think only for logs. I'm going to remove this to make it less scary. Okay, and this is a hello world program. Where is the code? Okay, the host code, the ZKVM or approver runs on the host. The host code is located in hello world src main.rs and hello world src lib.rs. The host creates an executor environment. So I guess I can see this. This is creating an executor environment before constructing a prover. Okay. This executor environment is responsible for managing guest readable memory. The host makes the value inputs available to the guest program. So I can see the value A and B are being passed, okay, available to the program, uh, available to the guest program before execution by adding inputs to the executor environment. Okay, prover is default prover. Okay, when the prover executes the program, it can access inputs by a dot write method on executor environment builder. Okay, when the prover executes the program. Okay, step 3, guest read the input and commit output. So this guest will read the input and commit output. Okay, this is a portion of the code that will be proven. In the code simple, the guest code reads the two A plus B values from the host and commits them to the journal portion of a receipt. I don't know where the journal will get generated. The environment function commits public result to the journal. Once committed to the journal, anyone with the receipt can read this value. Notice by committing any private information to the journal, we make this private data public. For this reason, be sure to avoid committing sensitive data to the public journal. Okay, let's look at how the host generates an hello world. This is guest src main multiply id tracing subscriber with environment tracing subscriber multiply. Wait, uh where did it getting hello world is fine. Okay, so this is the multiply default prover dot prove hello world methods. Wait, uh this thing, where is getting this hello world methods? Okay, so you'll get the elf from here. Okay, so we are describing this as a dependency. Okay, hello world methods. Multiply id. Okay, so this multiply is this one. Hello world method multiply elf, and this takes this elf. Nice. Okay. Let's look at how host generates the receipt. First receipt is generated, where the full multiply function is. Okay. Okay, so we can see cargo run hyphen release. Wait, wait. I know the factor of I know the factor of okay. Hmm. What if we can 22. Okay. Okay, so we can join the Discord definitely, but let's just move on to understand the input output. In the Hello World tutorial, we had a brief introduction to how to perform IO operations in the ZK VM. Now we will dive deeper into the subject. Okay, keep reading to learn more about it. Okay, I think it's good time to take a break. Okay, or we can just, uh, Okay, let's continue. Yeah, feeling re-energized after a really good dinner. Okay, so now now what? So we have run this Hello World tutorial. Okay, and yeah, I mean this code somehow is making a bit of a sense. So this is the main method that loads the two values from the host. Okay, and it verifies neither of them are one. Okay, and commit. Let's try to change this so that we can, verify if this age is adult, is adult. So how does versus what is doing? Okay, is adult is equals to age greater than 18. Okay, and can I commit this? Can we directly commit this? Why do I need to pass a reference? So I've changed this circuit. Okay, and can we can we go to guest cd methods guest. Okay, and yeah, cargo build or cargo run. Because I believe it should be possible, even though the name is multiply. Ah, so that means we need to provide a reference. That's what it says, at least. No, no global memory provider is provided. Okay, let's see if this still works. Hmm. Cargo, what about cargo build? Okay, I think I found this thing issue because you can't run this, right? This is not, you can't run the sketch program directly. That's why that was the issue. This is still the issue. Could not, no global memory allocator. No global memory allocator. Okay. Mm, this is. bit odd. Cargo run. So, I mean, we are able to run this particular code, but we are not sure. We are not able to change this. That is bad. Mm, understanding IO, understanding ZKPM data model. That's fine. Mm, but can't I build this? Then how do I check it? CD guest methods. Cargo build. How do I build my guest program in isolation? Ah, okay. Hmm, let's see. Age. So this is the age, and we comment this. Okay, that is adult is equal to age greater than 18. That's fine, and we commit a reference to adult. That is our entire guest program. Now let's try again. CD guest. We first do cargo build. That is not successful. Cargo check. Okay, so there is still this no global memory allocator issue. Now let's go one step above. Cargo build. Nice. So this build is working fine. Okay. And do we get anything out of this build? Incremental dependencies build. Okay. Cache directory. That is fine. What about cargo run? Cargo run is not there. That is fine. I think we are done with this thing. So now let's try to go one step above and do cargo run hyphen release. It should fail. It should, I think, not find this ELF. So there is this issue. Now we should 90. Okay, and this multiply is coming from here, and this is taking multiply ELF. Let's comment this. Okay, I think this should fine. They haven't changed the name, so I'm just curious if this will work. Hmm. Uh, the thread main panicked. Deserialize. On the deserialized side, there is some issue. Though we haven't changed the where does he get this ELF thing? Wait, where where is he's getting this multiply ELF? Like, how do you get this multiply ELF thing? Hello world methods. Mm, a prover dot prove. Ah, this one. Receipt dot default prover. This is fine. Where do we provide anything else? We just provide the name and commit the value. Okay, and here journal dot decode. Mm, okay, cargo test. It should give some error like false is not equals to, something false is not equals to. But yeah, I mean, this definitely is similar name exists. Okay, let's just do this. Test definitely failed. Journal output prover.prove right and a multiply ELF. Where this multiply ELF is coming from? Methods. Examples. Target. Risk we guessed. Okay. There is something wrong with this. Okay. Definitely. Okay, so this is proof composition, rest resources, fine. Now we need to see. Now I'm just basically tired. Okay, I am going to stop this stream and try doing things tomorrow.